Welcome to the deep dive. Today, we're digging into a set of materials you sent over study guides, briefings, FAQs, and even parts of the research paper itself, all about this new AI foundation model, Magma.
That's right. And Magma is, well, interesting because it's not just another model for looking at images or reading text. The sources make it clear its goal is different.
Different how?
It's built to understand and act in visual environments. So fake websites, apps, or even controlling a robot in physical space.
Ah, okay. So it's tackling that gap we often see. Like AI can describe a picture perfectly fine, or summarize text, great understanding.
Exact.
But getting it to then say, click a specific button on that website based on the understanding, or move a robot arm, that's a whole other ballgame.
Precisely. And this deep dive, our mission really is to unpack the academic advancements in these sources that let Magma do that.
Okay.
It's about how it blends what they call verbal intelligence, that understanding part, with spatial-temporal intelligence.
Spatial-temporal, so space and time.
Yeah, reasoning about space, time, and crucially, action. How to act to achieve something.
So we're looking at the core innovations, how it learns from really different data sources, right? Like clicking on screens and robots moving under one umbrella.
That's the plan.
Yeah.
What's the technical secret sauce here? What makes this fusion of understanding and action possible, according to the research?
All right, let's get into it then. The sources jump right into this main challenge Magma tackles, this disconnect between normal multimodal AI, good at processing vision and language, and these agentic tasks that need actual action.
Yeah, think about it. You've got models looking at a screen, maybe saying, okay, there's a submit button there. That's the understanding part.
Right.
But the action isn't saying submit button. It's maybe predicting the exact 2D pixel coordinates on the screen for that button.
Okay.
Or for robotics, it's not understand pick up the cup. It's calculating the complex joint movements, maybe 7 degrees of freedom for the arm to actually grasp it.
7 degrees of freedom? That's basically all the ways the robot arm can move, right? Up, down, twist, bend. It's pretty complex spatial stuff.
Highly complex, yeah. And that's the core problem highlighted. The output needed for understanding is often text. The output for action is coordinates or trajectories or these joint commands. Very different formats.
And the sources say just mixing data didn't work, like throwing UI screenshots and robot videos together in one big training set.
Apparently not. It seems the models just got, confused. The conflict between needing to output text versus needing to output precise spatial data was too much.
Why the confusion?
Because the underlying representation of action was so different, text descriptions versus spatial coordinates. The models couldn't find a common ground, a unified way to think about action across these different domains. They needed something new at the data level itself.
Okay, so they needed a common language for action, basically, across different types of data.
Exactly.
And this is where the big innovations come in.
Yeah.
The first one mentioned is set of mark, SoM.
Yes, set of mark. That's the first key academic technique they introduce. It's specifically for action grounding.
Yeah.
In static visuals, mostly images.
Action grounding, like figuring out where to act.
Precisely. Pinpointing the exact location in an image where an action needs to happen.
Like putting a target on it.
Sort of, but more structured. First, they use other AI tools to find potential things you could interact with. Buttons on a web page, text fields, maybe even the location of an object a robot needs to grab, seen through its camera.
Okay, so find the interactive bits first.
Right. Then each potential spot gets a number, a numerical mark. They basically overlay these numbers on the image, often inside a little box around the object, so you don't just see a button. The model sees, say, button mark 3.
Ah, I see. So a static image, like a screenshot or a robot view, becomes vision language action data. The language says what to do, click submit. And the action isn't just submit, it's interact with mark 3.
Exactly. And mark 3 is tied to specific coordinates, x, y, on that image.
Okay, that's clever.
It really is. Because now the model isn't trying to predict text or coordinates. It's predicting a mark number and the coordinates for that mark.
A unified output.
A unified output format.
Yeah.
Whether it's a UI button or a robot grasp point, the model learns to output the same kind of thing. Mark X at location, X, Y. This makes the whole action grounding process much, much easier across these different domains.
Okay, so SoM handles the where-in static images, unified output. But actions often involve movement, right, over time. That leads to the second innovation, trace of mark, ToM.
Exactly. Trace of mark, or ToM, builds right on top of SoM, but extends it to dynamic video data. SoM grounds action in one frame. ToM deals with action that unfolds over time.
Like watching a hand reach for something in a video.
Yeah.
Or a robot arm moving.
That's the core idea, yeah.
Yeah.
Instead of marking static things, ToM tracks the movement, the trace or trajectory of important moving objects across video frames. Could be a person's hand in a how-to video, or the end part of a robot arm, the end effector. And the model isn't just trained to see this movement, it's trained to predict the future trajectory.
Predict the future path. Wow, that sounds like it forces the model to anticipate, to plan ahead.
That's a major benefit, the sources point out. By predicting future traces, the model has to learn about temporal dynamics, how things move, how actions play out. It learns to look ahead, essentially, which is critical for planning sequences of actions, especially in robotics.
Makes sense. Temporal reasoning. What's the other big plus for ToM?
It's a really efficient way to use all that unlabeled video data out there for learning actions.
Unlabeled video, like YouTube how-tos.
Exactly. Videos showing people doing stuff. They don't have neat text labels saying, move hand here, grasp this, but they show the action.
And predicting the trace turns that observation into training data.
Yes. Predicting the pixel path of a hand or object over, say, the next few seconds gives the model really strong signals about action, about movement, about goals, and crucially, compared to trying to predict all the pixels in future frames, which is super computationally expensive and captures tons of irrelevant background detail.
Right.
Predicting just the trace uses way fewer tokens, but it captures the essential action dynamics, often over longer time periods. It's a smart way to get action supervision from video without explicit instructions.
That's really neat, using observation to learn action more efficiently. The sources mention some tech details for generating these traces.
They did. Getting stable traces isn't trivial. They use things like advanced point tracking models, co-tracker was mentioned, that are good at following points robustly, and also techniques like homography transformations.
Homography. Sounds complex.
Yeah, basically it's a math technique to deal with camera movement. Think about videos shot from a person's point of view, maybe a head cam. The camera shakes around a lot.
Yeah.
Homography helps stabilize the video relative to the actual scene, removing that distracting camera jiggle.
Okay.
So the trace you get is really the object's movement, the hand moving towards a goal, not just the camera bouncing. It focuses the learning.
Got it. Isolates the important movement. And just to be clear, ToM wasn't used on the UI data.
Correct, because UI data is typically static screenshots, not continuous video of someone interacting. So ToM is for the video and robotics data.
Okay, so let's recap. So Trainibium for action location in static images, using marks and coordinates for unified output. ToM for understanding movement and planning in videos by tracking and predicting traces. How do they work together?
They create this unified pre-training interface, as the paper calls it, by converting action info from UI clicks or robot moves, single points or paths, into this consistent mark or trace format. The model can learn from all sorts of data using one consistent approach to action.
And the data set they use for this pre-training sounds massive and really mixed.
Oh, absolutely. About 39 million samples, the sources say. Hugely diverse. You've got UI navigation data, clicking on websites, mobile apps, things like C-Click, Vision to UI.
Okay.
Then lots of robotics manipulation data from big projects like OpenX Embodiment covering different robots doing different things.
Right.
And then tons of human instructional videos, Epic Kitchens, Ego 4D, something V2, just people doing stuff. Plus, general multimodal data like ShareGPT-4V to keep its basic vision language skills sharp.
Wow, that's everything from ordering online to a robot making coffee to someone tying their shoes?
Pretty much. And that diversity is crucial. Not just the types of data, but the range of tasks, the different verbs and instructions, locate, click, drag, pick, lift, pour. It pushes the model towards being a generalist, not just a specialist.
And some was used on most image data, ToM, on the videos and robotics.
That's the setup, yeah. Some for grounding across the board where applicable, ToM adding the temporal layer for video and robot streams.
So this diverse data, processed via SoM and ToM, gets fed into Magma's architecture. What's actually under the hood, model-wise?
It uses pretty standard but powerful building blocks for these kinds of models. For vision, they went with ComNext XX Large.
ComNext? Heard of that, a convolutional network.
Right. They chose it partly because it's good at handling images and video frames of different resolutions, which is important here. UI screenshots are often high-res, videos might be lower. ComNext handles that mix well.
And the language side?
They used LlamaMA 38B, a very capable large language model.
Okay.
So how does it flow?
Pretty typical flow. Visual input goes into ComNext, gets turned into visual tokens. These are then stuck together, concatenated, with the language tokens for the task description, like click the blue button.
Got it.
All that goes into the Llama 3 model, which works as a decoder-only LLM.
Decoder only. Autoregressive.
What's...
Quick reminder. Sure. Decoder-only models like Llama are great at generating sequences like text. Autoregressive just means it predicts the next word or token based on everything it's seen so far, the input and the tokens it already generated.
Okay.
But here, they adapted it. Magma's output sequence isn't just text. It can also include those special mark numbers and coordinates from SoM or the sequences of coordinates for traces from ToM. So it uses the LLM architecture to predict actions, too.
Right. So the magic isn't just the individual models, but how they're connected, and especially how they're trained with SoM and ToM on that unique data mix.
Exactly. The pre-training strategy is the core innovation.
Okay, the big question for any academic work. The proof? Did it actually work? What did the results show?
Yeah, this is crucial. The performance evaluations and especially the ablation studies provide strong evidence. Magma achieves state-of-the-art SOTA results on lots of benchmarks, particularly impressive in zero-shot settings.
Zero shot, meaning it performs well on tasks it wasn't specifically trained for, straight out of the box.
Precisely. Tested on completely new scenarios. The sources show it hitting SOTA on UI navigation benchmarks like ScreenSpot, Visual WebEnch, and on robotics, tasks like SimplerEnv, even real robot manipulation.
Wow.
And what's really telling is it often beats models that were only trained for UI or only trained for robotics.
That really suggests the generalized learning work, doesn't it?
It strongly suggests that, yes, that the spatial-temporal intelligence learned during pre-training actually transfers effectively. It learns something fundamental about interacting with visual environments.
They also mention efficient fine-tuning.
Right. Another good sign. When they took the pre-trained Magma and did just a little bit of extra training, fine-tuning on specific tasks like complex web navigation, mobile apps, different robot setups, it got even better. Again, often hitting or beating SOTA for those specific tasks.
So it learns well initially and adapts easily.
Exactly. It shows the pre-training provided a really solid, generalizable foundation.
Okay, but the real acid test, you could say, the core academic proof for SoM and ToM specifically, comes from the ablation studies.
Absolutely. This is probably the most critical piece of validation from an academic perspective. Ablation studies are where you remove parts of your system to see what happens.
Yeah.
So they ran experiments where they trained the model on the same big mixed dataset UI, robots, video, all of it, but without using SoM and ToM to unify the action outputs.
And the result?
Clear degradation, according to the sources. Performance on both UI and robotics tasks dropped significantly. The model didn't become a generalist. It actually got worse at each individual domain compared to specialized training. It couldn't reconcile the different action formats.
So it wasn't the diverse data that was the problem?
No.
It was the lack of a unified way to interpret action within that data.
Exactly. That's the key insight the ablation studies confirm. When they put SoM and ToM back in, performance didn't just recover, it jumped up to those SOTA levels. It definitively shows SoM and ToM are the enabling technologies here. They bridge that domain gap.
That's compelling evidence. And they link performance gains on specific types of tests back to this.
They did. They showed improvements on benchmarks, testing spatial reasoning, specifically things like B-Link, spatial evil, VSR, and also on video understanding, especially predicting actions in videos like Intent QA or MV-Bench. These gains point directly back to the spatial learning from SoM and the temporal planning learning from ToM.
It draws a clear line from the innovation to the improved capability.
Yes, it does.
Now, with any powerful AI, there are always questions about responsible use limitations. What did the sources say on that front?
They're pretty upfront. They acknowledge potential data biases like the instructional videos, maybe not representing global diversity perfectly.
Okay.
And they strongly emphasize responsible deployment. Magma is mainly designed and tested for controlled settings, UI simulators, robot labs.
Not just letting it loose on the web.
No, they specifically recommend human-in-loop oversight for real-world UI stuff, a person checking or approving actions.
Which makes sense. An AI that can do things automatically, there are risks.
For sure. They acknowledge that agentic models like this, models that can automate actions, inherently carry security risks. Not that Magma itself is presented as a vulnerability, but the capability could potentially be misused by bad actors, maybe with different training data, for harmful automated tasks online. It's a general caution for the field.
Okay. So, pulling back then, what's the main academic takeaway from this deep dive into Magma?
Based on these sources, Magma is a really significant step academically towards generalist AI agents. The core contribution is how it successfully merges verbal intelligence, understanding language and visuals, with spatial-temporal intelligence reasoning about space, time, and action.
And the key enablers were those novel pre-training methods, SoM and ToM.
Precisely. They provided that crucial bridge, that unified representation of action, allowing the model to learn effectively from wildly diverse data. This leads to capabilities that generalize across digital and physical worlds in a way that wasn't really possible before.
It's a move towards AI that doesn't just see the world, but can, interact with it intelligently.
Yeah.
Which definitely leaves us with something to think about. What happens when AI can truly bridge that gap between just perceiving the world and actually reasoning about how to act within it physically or digitally? What new possibilities and what new challenges does that open up?